In the last section of the course, we generalized the idea of dot products to general vector space, and we managed to get angles, we got lengths, we got distances, and we also got orthogonal complement of a subspace. So in this section, what we'll try to do is we'll try to see how to generalize one of the constructions that we did in linear algebra 1, when we use a dot product to get projections onto vectors. Alright, so our goal, I'll just go through Rn first. So we started with a direction vector v. We took any vector we want here. D couldn't be 0, but otherwise there was no other restriction on it. And what we did is we decomposed v into two different vectors. One that's parallel. One that's parallel to d, which we call the projection. One that's perpendicular, which we call the orthogonal component. And one thing that we required was that when I say a decomposition of v, I need the sum of the two to be v. Alright, so it's really splitting v into two parts, one part that's parallel to d, one part that's perpendicular to d. Alright, so we're going to do this in any vector space. Actually, do I need... Alright, so our goal is for any inner product space so that's going to take the role of Rn. Now, instead of having a vector, we'll use a subspace. So in this case, it'll be the span of D, which is a line, but we could do more general, higher dimensional subspace. So for any subspace W of V, we're going to want two things. We want the projection onto W. This is a map from V to W. And we're going to want the projection onto the orthogonal complement. So I want these maps to be linear, and I want them to add up to V as there, as we had over there. So they add up to the identity. If you put a V in it, they add up to V. So here I would write that projection on D plus the orthogonal of D equals the identity on Rn. And here I'll say that the projection on W plus the projection on W perp equals the identity on V. Alright, so let me draw a picture of this, and then we'll see little by little all the tools we'll need to actually define both these maps. You can think of this orthogonal part as the projection onto the orthogonal subspace. And so let's draw it in R3, since that's the highest we can see. So if W is a plane. And then if I take V, well, in this picture, W perp will be a line and they're perpendicular. I'm going to take any vector V. And I'm going to split it into two parts. I'm going to have the projection here. And I'm going to have the projection on the W. And I'm going to have the projection on W perp. You could draw it here or draw it here. Projection on W perp. Okay. So same type of picture as before. The only difference is instead of giving you one vector to determine a direction, I'm going to give you an entire subspace. So already you see you'll have to do more work because you'll have to figure out which vectors in W to use, and that's going to be harder than it was in linear 1.